Label each of the following as a strong base, a weak base, or a species of negligible basicity. In each case, write the formula for the conjugate acid. Indicate whether the conjugate acid is a strong acid, a weak acid, or a species of negligible acidity. Acetate is a weak base. Therefore, its conjugate acid, acetic acid, is a weak acid. So if you are a weak base, you're something that doesn't take an H very strongly. It means you're going to make something that will give up an H. In a significant way, I should say. It's a significant acid. Hydrogen carbonate is a weak base, and therefore the conjugate acid is carbonic acid, which is a weak acid. So again, if you're a weak base, it means you're not that great an H taker, and therefore a significant H giver. Now, oxide is a really strong base. Therefore, its conjugate acid, hydroxide, is a non-acid. So this is not an acid. You're not going to get the H off of hydroxide in any normal way. D, chloride ion, is the conjugate base of a strong acid. So therefore, it's a non-base. You put chloride ion in the water, it doesn't do anything to the water. Whereas, because it's the conjugate of a strong acid, so it's a really lousy H taker. Ammonia is a weak base. Since it's a weak base, it has a significant weak acid as a conjugate acid, ammonium ion. Predict the products of the following acid-base reactions and predict whether the equilibrium lies to the left or the right of the equation. In other words, is it a spontaneous reaction or not a spontaneous reaction? So when I react oxide with water, water is going to act like the acid and protonate oxide to make two hydroxides. This is a very spontaneous reaction. Oxide is a strong base, and if you're strictly looking at acid strength, hydroxide is no kind of acid. So equilibrium will lie to the side of the weaker acid. Acetic acid with hydrogen sulfide. Now this one's harder. The conjugate acid of hydrogen sulfide is hydrosulfuric acid. So which is a stronger acid, acetic acid or hydrosulfuric acid, right? Where equilibrium will lie to the side of the weaker acid. So it turns out acetic acid is a stronger acid than hydrosulfuric acid. So this will be a spontaneous reaction, but not by much. Hard to tell on this one. You'd have to look at the Ka values. Nitrite reacting with water. Water's acting like the acid, so the conjugate acid of nitrite is nitrous acid. And hydroxide. All right, so the conjugate base of water is hydroxide. So this is going to be a very non-spontaneous reaction. As soon as you build up nitrous acid and hydroxide, the reverse reaction is going to take over and stop the reaction. Write the chemical equation that illustrates the autoionization of water. So this is water breaking apart to form H plus ions and hydroxide ions, or two waters reacting together to make hydronium ion and hydroxide ion. Write the expression for the ion product constant for Kw. Why is water absent from this expression? Well, liquids and solids do not appear in equilibrium expressions, so this is why it's called the ion product. There is no denominator. All right, so products of reactants raise their stoichiometric coefficients. We leave water out of this. We call this the ion product, Kw for water. Is a solution described basic? Oh, a solution is described as basic. What does this mean? It means you got more hydroxide in the solution than H plus ion. So this would be a basic solution. Higher concentration of hydroxide than H plus ion. Calculate the H plus concentration for each of the following solutions and indicate whether the solution is acidic, basic, or neutral. A, you've got an OH concentration of 0.0045 molar. Okay, so the way we figure out what the H plus concentration is we use the Kw expression, right? Kw is equal to 10 to the minus 14. So it's a constant, right? As the concentration of hydroxide goes up, the H plus concentration has to go down if I'm going to be equal to this autoionization of water constant. So with a very large concentration of hydroxide, well, it's larger than 10 to the negative 7, I get a very low concentration of H plus. So I divide the concentration of hydroxide on both sides and get the H plus concentration. Solution in which the hydroxide constant, B, the hydroxide concentration is 8.8 times 10 to the minus 9. Well, 10 to the minus 9 is lower than 10 to the negative 7, which is what you would get with a neutral solution. So as the OH concentration goes lower than 10 to the negative 7, that means the H plus concentration is greater. So when I divide both sides by the OH concentration, I get the H plus concentration, which is greater than 10 to the negative 7 now, right? Which would be the neutral solution. A solution in which the hydroxide concentration is 100 times greater than the H plus concentration. All right, so we're dealing with exponentials here, right? 10 to the negative 6, 10 to the negative 5. We're talking about powers of 10. So in order to get a hydroxide solution 100 times more concentrated than the H plus concentration, you'd have to have, 2 factors of 10 greater. So 10 to the negative 6 is 100 times greater than 10 to the negative 8. If sodium hydroxide is added to water, how does the H plus concentration change? Well, as the hydroxide concentration goes up, the H plus concentration goes down. How does the pH change? Well, as the H plus concentration gets smaller, the pH gets higher. B. Use the pH values in figure 16.5 to estimate the pH of a solution with an H plus concentration of 0.0006 molar. All right, so you're taking the negative log of the H plus concentration, right? So you're turning this into a number that represents how many tens you got, right? So we're talking 1, 2, 3, 4. 4 positions to the right, all right, so the 10,000th position. So if I take the negative log of that, I'm talking like a pH of 4, maybe less than 4, something like that. So if I take the negative log of 0.0006, I get, about 3, over 3, pH of 3. All right, that's an acidic solution. C, if the pH of the solution is 5.2, first estimate, then calculate the molar concentrations of the H plus and OH concentrations in the solution. All right, so if I want to convert pH back into H plus concentration, I take the negative pH to the base 10, and that'll, put it back in exponential form. So if it's to the negative 5th power, all right, we're talking like a pH of like maybe 6, something like that. Or negative 5 at negative to the pH of 5, something like that. So, all right, so negative 6. So if we know what the H plus concentration is, we divide that into 10 to the minus 14 and get the OH concentration. So 10 to the negative 6, we're looking at an OH concentration of like 10 to the negative 8. Around. What is a strong acid? A strong acid completely ionizes when it hits the water. If a solution is labeled 0.5 molar hydrochloric acid, what is the H plus concentration in the solution? Well, it's 0.5. Completely ionizes. Which of the following are strong acids? Well, hydrochloric, hydrobromic, nitric, chloric, perchloric. These are the strong acids. Hydrofluoric is not one of the strong acids. Calculate the pH of each of the following strong acid solution, right? So if I know what the molarity is of the hydrobromic acid, I know the H plus concentration. So take the negative log of the H plus concentration and get the pH. B, same thing, right? If I want to know what the molarity of the solution is, right? So convert grams of nitric acid into moles and divide by liters to get the molarity. That's the same as the molarity as of the H plus concentration, right? It's a strong acid, so complete ionization. So take the negative log and get the pH. All right, so 5 milliliters of 0.2 molar perchloric acid are added to 50 milliliters of water. Oh, so this is a dilution problem, right? So, we dilute the acid, right? So M1V1 is equal to M2V2. We solve for M2, and that's the H plus concentration. Take the negative log at the pH. D, solution formed by mixing 10 milliliters of 0.1 molar hydrobromic acid with 20 milliliters of 0.2 molar hydrochloric acid. Well, both of these acids are contributing moles of H plus, right? So, multiply the little typo there I had to address. So now we have the molarities of the hydrobromic acid and the hydrochloric acid. We multiply by how many liters each of these solutions were. So 10 milliliters is 0.01 liters, 20 milliliters is 0.02 liters to get moles being contributed by each of these acids. And then you add them together to get the total moles of acid when I mix these together. Right? So it's a cumulative effect. The chloride ion and the bromide ion are spectators here. So just add up moles of H plus, divide by the total volume, right? The new volume is now 30 milliliters to get the concentration of the H plus concentration of H plus, and take the negative log and get the pH.